Everyone. um, Today I begin with direct kinematics. In my last presentation, I talked about homogeneous transformation. So we discussed about how can we transfer not only the pose, the orientation, but also the distance from the origin. So something like that. So if this frame is at the distance of 0.01, so how can we include this factor in our transformation as well? So we ended up having homogeneous transformation. So today I'll talk about direct kinematics. Um, a manipulator consists of a series of rigid bodies, which we call links, connected by means of kinematic pairs or joints. Joints can be essentially two types, which are revolute, like this, and prismatic, like this one. So this one is the symbol for prismatic joint. Um, A conventional representation of two types of joints are sketched in this figure. The whole structure forms a kinematic chain. The aim of direct kinematics is to compute the pose of the end effector as a function of the joint variables. So this is the main function. One end of the chain is constrained to a base, okay, and and an end effector, which is gripper or tool, is connected to the other end, allowing manipulation of object in space. From a topological viewpoint, the kinematic chain is termed open when there is only one sequence of links connecting the two ends of the chain. Alternatively, a manipulator contains a closed kinematic chain when a sequence of links forms a loop. The mechanical structure of a manipulator is characterized by a number of degrees of freedoms, which uniquely determines its posture. Each degree of freedom is typically associated with a joint articulation and constitutes a joint variable. The degree of freedom of a system is the number of independent parameters that define its configuration. It is the number of parameters that determine the state of the physical system. So let's let's begin with let's continue with that. It was previously illustrated that the pose of a body with respect to a reference frame is described by the position vector of the origin and the unit vector of a frame attached to the body. Hence, with respect to a reference frame called OB, which is body frame, the direct kinematics function is expressed by the homogeneous transformation in which we are moving from end effector to body frame. So here we have some n factor, some s factor, some a factor, and some p factor. And I'll talk about this, where q is the n cross 1 vector of joint variables n e b, s e b, and a e b are the unit vectors of frame attached to the end effector, and PE is the position vector of the origin of such frame with respect to the origin of the base frame. So this one, okay, let me zoom that for you. Okay, so this one. Um, Note that NE, SE, and AE and PE are function of Q. The frame OB, which is the body frame, XB, YB, ZB, is termed as the base frame or the body frame. The frame attached to the end effector is termed end effector frame and is conventionally chosen according to the particular task geometry. If the end effector is a gripper, the origin of the end effector frame is located at the center of the gripper. Okay, and the unit vector AE is chosen in approach direction. So this one is in approach direction. The unit vector SE is chosen normal to AE in the sliding plane, like this one is the sliding plane, and the unit vector NE is chosen normal to the other two uh, 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 other two axis so that the frame NESEAE is right-handed. So it's a right-handed frame. So I'm sorry. Okay. So here's an example. Consider the tooling planar arm in figure this 2.14. On the basis of simple trigonometry, the choice of joint variables, the base frame, and the end effector frame leads to equation 2.49, which is this one. So we have this normal sliding and approach and then position. So we have this PE, and we could end up having this S12 C12 minus C12 S12. So we could reach by this. If we want to move from here to here, angle theta 1 and angle theta 2, if you combine them together, it becomes sine 1 2 and then minus cos 1 2. Okay, because this rotation is being occurred in, wait a minute. Okay, I was thinking about this explanation. So first of all, this NE is nothing more than the z-axis 0, 0, 1. So the rotation is going to be taken place along this axis. And then we want to move from this frame to this frame. So how can we align it? So if you see that this AEB, this one is parallel to this one, and this one, if you rotate XP and along this one, so this is going to be theta 1 and theta 1 plus theta 2. And in the same way, if this is going to be the Y and sliding axis, so if you want to move from this axis to this axis, again theta 1 plus theta 2. So that's what we're going to get if you consider these rotations. So we're going to end up with this rotation matrix. Again, the end effector location from here to here is gonna be is simple trigonometric function, which is a1 cos theta 1 and plus a2 cos theta 1 2, which is this one, and then a1 s1 from here to here, and then a2 s1 2, so it is gonna be a1 s1 2. So from this one is gonna be like this. So this one is PEB. Um, that's how we're gonna get this matrix. Now let's talk about open chain. Consider an open chain manipulator constituted by n plus 1 links here, connected by n joints. So we have n plus 1 links and n joints, where link 0 is conventionally fixed to the ground. So this way link is fixed to the ground. It's kind of it is assumed it's kind of fixed, and yeah, that's what it is. I'm not going to comment anything more than that. It is assumed that each joint provides the mechanical structure with a single degree of freedom corresponding to the joint variables. Okay, the construction of an operating procedure for the computation of direct kinematics is naturally derived from the typical open kinematic chain of the manipulator structure. Sorry. um, in fact, since each joint connects two consecutive links, it is reasonable to consider first the description of kinematic relationship between the consecutive links, and then to obtain the overall description of manipulator kinematic in recursive fashion. So what I'm going to do is first move from this position, from this frame to this frame. If we can do this successfully, then we can do the rest of the transformation. So to obtain the overall description of a manipulator, kinematics in a recursive function, it is worth defining a coordinate frame attached to each link from link 0 to link n. So this one is from link 0, and then this one is link n, and the next link is going to be the link n plus 1. Always remember, there are n plus 1 links for n joints. So this one is nth joint and n plus 1 link, and then coordinate transformation describing the position and orientation of frame n with respect to frame 0, and you can pretty much define it like this. So overall transformation from frame 0 from to n is can be defined like this. So we have n to n minus 1, then n. So again, remember that we have n plus 1 links, but we have n joints. So we're moving, and we believe that our reference frame is located at the joint. Okay. So open chain with reference to the direct kinematics equation in 2.49, which is this one, and the actual coordinate transformation describing the position and orientation of the end effector frame with respect to the base frame can be obtained as this. It's the end effector to base frame. So there's going to be what is that, from link 0. Okay, so from link 0, so we move from link 0 to base frame. Sometimes it is sometimes we make a frame which is fixed, and let's call this base frame, but on the top of that there is a joint which can move, so we call this a zero frame. So from zero joint, or zero joint, because there is no length attached to it. So then from 0 we move to nth frame, and then from nth frame we move to end effector, where TB0 and TNE are two typical constant homogeneous transformations describing the position and orientation of frame 0 with respect to base frame. Okay, so T0B is quite of constant, and base frame and effector frame with respect to frame M respectively. So sometimes we're going to make this kind of notation that there's a base frame which is different than the in a zero frame. Okay. With reference to figure 2.16, let axis I, let me show that this is axis because this is joint I plus 1, and let axis I, so this one is gonna be my axis I, denote the axis of joint corresponding to link I minus 1. So this one is link I and this one is link I minus 1, and the so-called Denavit Hartenberg convention DH is adopted to define link frame I. So this one is axis I, previous one is link I minus 1, next to it is link I. Choose axis ZI along the axis of joint I plus 1. So this is joint I plus 1. So this is going to be my ZI axis with the common normal to axis zi minus 1. So this one my zi minus 1, and then I locate the origin OI at intersecting of axis zi and with zi minus 1. Okay, so that's how I'm gonna intersect, and this is gonna be my intersection point, and I'm gonna locate, call it OI, origin frame for I. Interesting to note that axis I has the origin on the net on attached to the link, and that link attached to the joint. So we're gonna have this axis origin over here. Okay. And then choose axis xi. So this is gonna be axis xi along the common normal to the axis zi minus 1. So this is common normal, and with the positive direction from I, from joint I to I plus 1. So this I to this one is positive direction. Then let's go further. The Denavit Hartenberg convention gives a non-unique definition of the link frame in the following cases. So in the following cases, it's going to give us non-unique um, definitions. In all such cases, the indeterminacy can be exploited to simplify the procedure. For instance, the axis of consecutive frames can be made parallel. So we're gonna make it. We can exploit these properties and simplify our procedure. For frame 0, only the direction of axis Z0 is specified. Okay, then O0 and X0 can be arbitrarily chosen. So for example, for this is I'm gonna make this frame 0. We can, and direction of X is specified, so I specify only this direction. Then O0 is specified, then O0 and X0 can be arbitrarily chosen. So we can choose X0 and O0 arbitrarily. For frame N, there is no joint N plus 1. So if this is N, then N plus 1, there is no joint. Zn is not uniquely defined. So in this case, this Zn is not uniquely defined. So you can define it in any way you want. While xn has to be normal to axis zn minus 1, so this axis has to be normal to zn minus 1. Typically joints n is revolute, and thus zn can be aligned with the direction of zn minus 1. So if you don't know there is no joint, you can align n, this zi, with zi minus 1. When two consecutive axes are parallel, so like this one, the common normal between them is not uniquely defined. So the common normal, you don't need to, there is no way to define a common normal in a unique way. You can define it in a different ways. When two consecutive axes intersect, the positive direction of xi is arbitrary. So when two consecutive axes intersect, okay, the positive direction of xi is arbitrary, so you can choose any direction from here to here or here to here, when there are the consecutive axes. When joint I is prismatic, so if this joint is prismatic, only the direction of zi minus 1 is specified. So only we specify the zi minus 1 direction, and the rest of the directions are calculated accordingly. Once the link frame have been established, okay, the position and orientation of frame I with respect to frame I minus 1 are completely specified by the following parameters. Okay, so once the link frames have been established, um, so AI is the distance between OI and OI dash. So this is the distance. You can see that this is OI dash and this is OI. And the distance between these two frames, two regions, is AI. DI is DI coordinate of OI along ZI minus 1. So this is going to be, sorry, this is OI dash. So this is OI dash, this is DI. Okay. So I'm going to put this dash over here, this one. Okay, alpha I denote the angle between axis zi minus 1 and zi about axis xi. So what we are doing is we are rotating zi minus 1 to in about axis xi to rotate and to make it form like this. So we are rotating x zi to zi minus 1 about axis xi. Okay, from here to here, from zi minus 1 to zi. So this is alpha. Theta angle between the axis xi minus 1 and xi about axis zi minus 1. So this is the angle theta. Okay, so what are we going to do? We are going to rotate this xi minus 1 to xi. So this rotation along zi minus 1 gives us theta. If joint I, this one is revolute, the variable is theta I. If joint I is prismatic, the variable is di. So if, for example, if this one is revolute, so this rotation would be possible. If joint I is prismatic, so this movement would be possible, and this would be the variable. Now let's express the coordinate transformation from frame I and frame I minus 1 according to the following steps. So let's consider this is frame I minus 1. As I said, that this is axis I. The axis I frame would have in the next joint, and axis I would have the I minus 1 frame over there. Choose a frame I, choose a frame aligned with frame I minus 1. Okay, first of all, translate the chosen frame by di. So first of all, align it with I minus 1, and then translate the chosen frame by di. So we are moving from here to here, along axis zi minus 1. So this is zi minus 1, along axis we're moving from here, and rotate it by theta I. So then we're gonna rotate it by theta I, like this, about axis zi. This sequence aligns the current frame with frame I, and is described by homogeneous transformation. So I'm sorry, this is gonna be frame I dash. Okay, okay, I have corrected it. So okay, so I have corrected this with I dash, and now we have this transformation matrix, this rotation matrix here, and we are moving from I dash frame to I minus 1, which is I dash to I minus 1. So we have this d1 for transformation because the transformation has occurred along z axis, so from here to here. Now translate the frame, align frame with frame I by AI. So now we are here. Now we from here we want to move from here to here. So what we're gonna do is we're gonna frame I by align with frame I by AI. So this is AI along axis xi. So we are because we are moving along x-axis. So this rotation matrix would be, we are rotating along x-axis. So this rotation matrix will be based on x-axis, and then as we are moving along this x, so this is gonna be the transformation. So AI is the transformation. So in this way, we are moving from I to I dash. Okay. And the resulting coordinate transformation is obtained by post multiplication of the single transformation, as like this. So here first we move from I to I dash, then from I dash to I minus 1. So overall I to I minus 1. Notice that the transformation matrix from frame I to frame I minus 1 is a function only of the joint variables Qi. That is theta for a revolute joint, or di for a prismatic joint. So we have this kind of relationship. Okay, to summarize, the Denavit Hartenberg convention allows the construction of the direct kinematic function by composing of the individual coordinate transformation expressed by 2.52, which is this one, into one homogeneous transformation matrix as in 2.50, which is this one. This one, okay, from 0 frame to nth frame. The procedure can be applied to any open kinematic chain and can be easily rewritten in an operating form as follows. First of all, find and number consecutively the joint axis. Set direction of axis from z0 to zn minus 1. So if you're going to choose this one as z0, then you're going to choose this zn minus 1, and then so on. Choose frame 0 by locating the origin on axis z0, and axis x0 and y0 are chosen so as to obtain a right-handed frame. So this should be the right-handed frame, and if feasible, it is worth choosing from 0 to coincide with the base frame. So if you're gonna coincide, if feasible, if this is feasible, you just choose it with reference to the base frame. Okay. Sometimes the structure is quite odd. It's like at angle and some different with some angle and with some length with respect to base frame. So sometimes it is not visible, but if it is visible, it always makes things easier. Now execute steps from 3 to 5 for I. Join from I to I minus 1, to I, from I1 to I to n minus 1. So from this is axis I to I minus 1 and to n minus 1. Locate the origin OI. So first of all, locate the origin OI at the intersection of ZI. This one is ZI with the common normal axis to axis Z minus 1. So this is my ZI minus 1. So this one into this one. So this is ZI minus 1. So I'm gonna common normal is this one. If axis Zi minus 1 and Zi are parallel and joint I is revolute, okay, then locate OI so that DI is equal to 0. So if these two axes are parallel and these joints are revolute, so this D make sure that DI is 0. If joint I is prismatic, locate OI at the reference position for the joint frame, that is range and mechanical limit. So if the joint I is prismatic, which means it may move in this direction. So then in this case, locate OI is this one at the reference position. For example, if this one move from this position to this position, this one is the maximum limit. So choose this one normal to here. Okay, so this one would be the OI. Choose X. This would make our problems a lot simpler when we're gonna develop the transformation matrix. So choose xi along the common normal to axis zi minus 1 and zi. So this one gonna be x-axis xi with the direction from joint I to joint I plus 1. So from joint I to joint I plus 1. So this is gonna be the positive direction. Choose axis yi so as to obtain right-handed frame. So this one is to make the right-handed frame. Now to complete, choose frame n. If joint n is revolute, then align Zn with Zn minus 1, already discussed. Okay, if these two frames are, if this joint is revolute, then make them, then align them and make them parallel. If joint n is prismatic, okay, then choose Zn arbitrarily. You can choose Zn arbitrarily, and axis xn is set according to step number 4, which means the axis is set at based on the description given in step number 4, which is to choose OI in the position where it has the limit, with this limit of its motion in prismatic fashion. For I equals to 1 down to n from table of parameters, form the table of parameters AI, DI, alpha I, and theta I. Again, theta I is the rotation along Zi minus 1. Alpha I is the rotation along x-axis, along this one. Okay. No, theta 1 is along Zi minus 1, and alpha I, which is this one, is along x is along okay. Remember that this rotation is along Zi minus 1, which is this one, and this rotation is along x-axis, which is this one. Okay, and di is the distance of this frame if we move from this frame to this frame location, and AI is the distance if we move from this frame to this frame. So these are the two intermediate, this is the intermediate point between if you're moving in between these two frames. On the basis of the parameter in 7, compute the homogeneous transformation matrix from I to I minus 1 for I up to 1 down to n. So from 1, okay, so first 1 to 0, and for example from 4 to 3, 3 to 2, 2 to 1, and then 1 to 0. So that's why this is the way we're gonna choose these transformation matrices. Then compute the homogeneous transformation T0 frame 0 to frame n, like this, from n to n minus 1, then n minus 1 to n minus 2, and finally from 1 to 0. That yields the position and orientation of frame n with respect to frame 0. And then given T0b, which is from frame 0 to base frame, and TEN from n factor to nth frame, compute the direct kinematics function as T0B, D end effector B, D end effector to base frame like this. You move from end effector to nth frame and then from nth frame to 0 and then 0 to base frame. This yields the position and orientation of the end effector frame with respect to the base frame. For what concerns the computational aspects of direct kinematics, it can be recognized that heaviest load derives from the evaluation of transcendental functions. So the difficult part is this one, heaviest load, transcendental function. Okay. On the other hand, by suitability factorizing the transformation equations and introducing local variables like the number of lobes, addition plus multiplication can be reduced. So we can reduce number of multiplications. Finally, for computation of orientation, it is convenient to evaluate the two unit vectors of the end effector frame of the simplest expression and derive the third one by vector product of the first two. So this is a very easy way to do that. Um, okay. So I'm gonna stop my presentation here, and I would continue in my next lecture about this description. This is connecting of a single link in the chain with two links. So we have one link and then we have two links. So how are we gonna do that? We're gonna discuss about this later. So for today's session, this is the end of my presentation. If you have any question, please comment below. Please subscribe to my channel and keep this discussion up and running. I appreciate your kind presence and everything. I appreciate your kind attention. Thank you.